So here is the website I just read from. As I said before, if you go to this website, you can click on these links that will take you to notebooks that I will show in just a minute. Let me start with a few slides just to introduce the topic really from scratch. So deep learning is a field of machine learning. Machine learning is a field of statistics, a field of computing that focuses on learning from data. And learning from data means that we can extract certain features from the data, or we engineer them, we select certain features of the data, and then we use a set of training data to look at those features and infer something, model parameters that then tell us something about these data, their properties, and for example, the examples that you've seen just before. And then we strictly separate out a separate test data to evaluate the accuracy of these models, and that's something that we really need to do when we're doing deep learning, because these models have a very large number of parameters, a lot of degrees of freedom. Artificial neural networks are a family of machine learning algorithms. They're sort of biologically inspired. This is from the work Vince, in his timeline, he had way over on the left work from the 1960s on so-called perceptrons. Minsky and Papert wrote a book about that, and they have this image that I really like that sort of shows how there are neurons on this side looking at the world, and then it turns into math over here on that side. This is another kind of representation of neural networks. You might think of input units at the very bottom sensing the input data. For example, this might be pixels or voxels of some imaging data, each one of these input units, and then the information propagates to hidden units in the network through a set of weights. So each hidden unit here sums linearly over its inputs, and then it can transform this data through maybe some nonlinear operations. Those might be nonlinear transformations within this, or pooling across different units. And then this happens again in another set of hidden units, and there may be many, many layers of hidden units, which is why these models are sometimes called deep networks. And then finally, there are output units here. These might be of the kind that say, oh, for example, this was an image of a cat, and or if this one is active, this was an image of a dog, or it might be something more continuous. And learning in networks is done by backpropagating the errors. So we learn by looking at the data and then assessing cost function. For example, did we get how many of the data points that we're currently showing did we get right? If we didn't get a lot right, then we need to somehow tell the network about this. And the way that happens in neural networks these days is by a process called backpropagation, which we will look at in a little bit of detail in just a few minutes. The idea is you might think there's a daemon inside of this, in this network, and it goes from node to node and from weight to weight and adjusts those in some way. And this diagram, I should say, comes from a wonderful online book by Michael Nielsen that really lays this out both in simple language, but also in mathematical terms. So if you want to learn about neural networks, that book, I recommend that book. And so for the top layer, we look at how would the error change, how much better would we do if we change the activity in each unit just a little bit. And we can do that at the top layer because we have access to the errors of the top layer. If we go further down into the network for layer L-1, we need to ask how much would a change in each weight affect the activity in the following layer, layer L, the layer one above that. And that depends on how active is the node feeding into this particular weight. How would a change in the weight affect the output of the node it feeds into? And then how is the activity of this node affecting the error? And we'll see this in detail in a little bit more fleshed out in code, this algorithm, in just a few minutes. And then the second part of training the network is what's called stochastic gradient descent. In stochastic gradient descent, you choose some random batch from your training data, you calculate the errors from the top of the network back propagating through, and then you adjust the weights by a small amount, and you repeat that until the network converges. This is what it looks like graphically. Imagine that we only had 2 weights in our network. The x-axis is the first weight, and the y-axis is the second weight. And the blue and red here are not known to us in advance, but are the errors of the network. And we start by just initializing the network to some random value of these weights, and then we let the backpropagation process explore this and go down the gradient. Notice that the process of stochastic gradient descent doesn't go smoothly directly to the minimum, and that's because in each iteration through, we're looking at a different set of data, and this data might be noisy, and some of the data tells us to go over here, and some of the data tells us to go over there. But overall, the data pushes us towards this minimum of the error, and eventually it converges and settles down there, and then we might stop the learning. So that's the process of stochastic gradient descent. You heard about convolutional networks. We'll look at a bit of examples on convolutional networks in just a few minutes. It's interesting to note that they're inspired by our visual system. Neural networks in general are inspired by the biology of our brain, and convolutional networks are in particular inspired by the visual system. Here's an image of the physiology of the nervous system in optical imaging recordings, where you can see that each part of the brain represents different orientations. But another way to think about this is that for each orientation, there is a filter that explores the full visual field. So you might think that it's more like this. If you think of this 3x3 array down here as a filter, for example, a filter for horizontally oriented lines, that filter is then passed over the entire image in what is a convolution to extract this green image up here. So the blue is the input image, and the green up here is the extraction of this convolution into what we call a feature map within the neural network. And so here's an example of a convolution of an image. If we take this image of a wall, and we take this filter that has a horizontal line in it, then you see that this prefers certain parts of the image. When we filter this image with this convolutional filter, we get parts of the image are emphasized that contain horizontal lines. And if we take a vertical line instead, you'll see that parts of the image that contain vertical edges are emphasized by this. And this is learned automatically by artificial neural networks. These kinds of filters are learned automatically by the networks. And these networks have been really, really successful in tasks like, for example, classifying different images this is the landmark paper in 2012 that Vince was referring to before that really brought these methods to the fore. So, okay, I'm going to switch over now to a computational notebook that you can run on your laptops as well. If you go to the link that's in our schedule here and click on this, it will take you into this environment called Colab, and hoping that the Wi-Fi works for us here. Maybe I'll stop mirroring so that I can see what I'm doing. All right. So this is called the Jupyter Notebook, and it contains code, it contains some text. Each one of these sections of this notebook is called a cell, and you can execute this cell by typing Shift and Enter. And the first cell here will get some, it'll warn you that the notebook was authored by me and not by Google. I'll tell it to run it anyway, and it'll reset my run times. I will approve that. When running things in this environment, you want to make sure that the runtime type selected by going to runtime and change runtime type, you want to make sure that it's a GPU. Graphical processing units, the things that we use to run graphically demanding computer games, have become really, really useful in neural networks as well, because they can accelerate some of the computations, like convolutions, that we do. And so it's really important when trying to do deep learning and using artificial neural networks in computations to use GPUs, because otherwise things are really, really slow. At the top here, I'm executing some code in Python to import components. I will make this larger so that it's visible. How's that? Can you see that back there? Somebody? Yeah? Okay, good. So I'm importing some modules that I'll be using. And as a first example, let's look at a really, really simple neural network that I've diagrammed up here. It's got two input units, x11 and x12, and two weights leading into an output unit. And so I can write this out. So the way this network works so far, it's very, very simple. So the way it works is that the output is a linear sum of the inputs. X11 times this weight and X12 times this weight. So the activity in the input units is summed linearly. Implementing that in some Python code, I set the weights to be some values and then implement this equation in simple arithmetic in Python code, and I can print the output. It's 4 in this case. More generally, the output of any unit is a dot product between its weights and the activations of the units impinging on that unit. So here I'm implementing this as a dot product and doing the same, and the result is the same. A multi-layered network will have a hidden layer like here, right? So this is a very simple multi-layered network. It's got the input layer as before, it's got a hidden layer, and so now every unit in the hidden layer receives weights from each one of the inputs. So you see this one receives through this weight 2,1 and weight 2,2, it receives inputs from X11 and X12, and this unit here receives through weight 1,1 and weight 1,2 inputs from these input layers. And then finally there's one output unit that sums from the hidden layer. So this sequential feed forward with one hidden layer. And so I'm implementing that here. I've initialized the weights, the activities of the inputs. Here I'm initializing the weights from the first layer to the second layer to the first hidden layer, and then I'm implementing the weights from that layer to the output layer. And to do the computation of the output of this network, I need to do 3 sequential dot products. Each line here in this first section is the dot product done by the units in the hidden layer, and then this is the dot product executed by the output, by the one unit in the output layer. And so first, these hidden layer activities are computed, and then these hidden layer activities are then taken as inputs into the output layer, and somehow miraculously this network also has an output of 4. Things get a little bit more interesting when the operations done by each unit in the network are not strictly linear operations. So it's very typical for units within deep learning networks to take the inputs, sum them linearly, and then operate on them through some function. Here it's designated through this through this letter F. So the function is operating on these linear sums. For example, we might have one that was really, really popular early on is this hyperbolic tangent, and that's because it looks like the activation of a neuron in our nervous system. This is the FI curve that you might recognize from basic physiology. But another function that's been used more recently is this one. This is called the rectified linear unit, and you'll see a lot of those today in a lot of the code that we'll be looking at. Rectified linear unit, if the linear sum of the activities going into a unit is less than 0, it sets the activity to 0. And if it's above 0, it takes that and passes that on. That's called the rectified linear unit. It's a very simple form of nonlinearity that can be implemented by neurons in an artificial neural network. Here I'm implementing that by taking the maximum between the dot product, that is the linear sum that goes into the unit, and 0. So if it's less than 0, it gets set to 0. And so when we do that, the output of the network is now different than it was before because each unit is now implementing a nonlinearity. As I said before, networks are trained through gradient descent. We gradually change the values of the weights of these weights. We're learning changes in the weights through observing known sets of input-output relationships. And the gradients are calculated. The gradients to change the weights are calculated through a process of backpropagation. Errors propagated back through the network to calculate a gradient, or you can think of it as a derivative on that error function that I showed you before as a blue and red map, by multiplying the following 3 numbers. The gradient of the loss function with respect to the node a weight feeds into, the value of the node feeding into the weight, and the slope of the activation function of the node it feeds into. So those are the 3 numbers that we need to know, and when we multiply those together, it tells us how much we should change the weight that we're considering at this point. So let's say, for example, that we have the network we had above, and let's assume that instead of 12, we want the desired output for the inputs that we put in to be 10 instead. So in this case, we take the simplest possible error. Our simplest cost function is the absolute difference between the output that we got from the network, x31, the output is the activity in the output unit, and 10, which is our desired output. We calculate the gradient of the activation function, or the derivative of the activation function, which is the slope of the activation function, which for the rectified linear unit is simply is a very simple function. If the number is larger than 0, it returns 1 because the slope of this function up here is 1. And if it's less than 0, we return 0, which is the slope of this rectifying part of the function. So this is the derivative of the slope. And so now we have the three numbers that I told you about. The first is the error with regards to the output. The second is the activity of the unit feeding into the weight. And then finally, the derivative of the activation function of the output unit. And so up here are the errors, or the gradients on the weights feeding into the top unit, the output unit. We propagate further by taking now the errors that we had up here and propagating those down through the networks. This is the process of backpropagation. So this is the error 311 that we calculated up here, and that one is multiplied by the activity in the previous units and the units in the input layer, and so on, the derivatives of the activation functions and so on. So we calculate all these errors here in the code. We set a very small learning rate. We're going to slowly go down this gradient, and so for each weight, we update the weight based on the error of that weight, the gradient of that weight, and multiply it by a very small error learning rate that we apply to that. And so here we're calculating the network again, and so now the activity of the network has gone further towards our desired output, which was 10, and then we repeat the process. We do backpropagation again, and so now the output is even closer, it's 10.1, and so on and so forth, until we've settled on the right or close enough to our desired output. So this was a very, very simple network. I'm next going to make things a little bit more complicated because it's not practical for us to write this kind of code every time that we want to do deep learning. Instead, we're going to use a library that implements this. The library that I'm going to show you here and that you'll see in a lot of the presentations later on today is called Keras. It relies on the TensorFlow library that Vince mentioned in his talk, but simplifies the programming interface into simple building blocks that you can use to build the networks that you want for your application. I'm going to make some data. I'm importing some libraries again. Here's some data. Here's some very, very simple data. I'm looking at an image, and it has only 2 pixels. So the first row here are the values of the 2 pixels in the image, grayscale values of the images of the values of the pixels in the first image. This is the second image, the third image, and so on. And notice that I've created training data, and I have training labels also. So here are the labels. The first image is of the second kind. Let's say those are dogs, and the first image is, the second image is of the first kind. Let's say that's a cat, and this is again a dog, and another cat, and another cat, and another cat, and so on. And I'm trying to classify those. Let's see how this data is laid out. You can see that this data, here in yellow you have the dogs, and in blue you have the cats, and on the x-axis you have the values of pixel number 1 in this 2-pixel image, and on the y-axis you have the values of pixel number 2. And you can see that it's linearly separable, but it's intermixed in some way, and that's what our neural network is going to try to disentangle. I'm going to use the sequential kind of model, and in my presentation here for now, at least the models are always going to be sequential, feed forward, and I'm going to import a kind of network model called a dense model, a dense network layer, and that means that every unit in the previous layer is connected to every unit in the layer that we're feeding into. So here I'm starting, this is what Keras data looks like. I'm initializing a model object here. I'm adding into the network a densely connected layer with 32 units. I'm telling it about the shape of the input. In this case, it's 2 pixels for the 2 pixels in the image. And then I'm telling it I would like a rectified linear unit, sometimes referred to as ReLU, as my activation for this densely connected layer. Then I'm adding another densely connected layer, and this is the output layer of my network. So this is a very simple network. It has 2 layers. in it, and the activation for that is called the softmax, and that's an activation function that helps us determine between different options of the output. I compile the model, I tell it to use categorical cross entropy as the loss. This is a loss function that's used for these kinds of classification problems, and I set some optimizer and I asked it to tell me about the accuracy as it's running. I should have run this first, and now I'm running that. And that constructs the model. And then using the training data and training labels that I have, I tell it, run this for 5 epochs. Epochs are how many times I run over the entire data. I tell it in each batch, take 100 of my points. This is in the stochastic gradient descent process. Each time I'm going to look at 100 data points and use that to go downhill. And then I'm going to look at every epoch. I'm going to look at 20% of the data that I've set aside, that I will set aside automatically as a validation data set. So that goes through and trains that on, and that went pretty fast because it's a very simple network, and it's not bad. It's doing 85% accuracy in this case. I can turn the model around to predict the outputs for some test data that I set aside in advance, and it can tell me what the prediction looks like. So here's a prediction in a set aside test data, again laid out in this spatial layout. I'm going to skip through this a little bit just because for the sake of time, just to tell you that if the data is not linearly separable, if the data looks like this kind of simple network will just not cut it and will give you this kind of prediction that is not that great. And for that, we need to add more layers. So here, I'm taking the same model that I created before and adding one additional layer into this, an additional densely connected layer here, and running this fit on that, and now it's doing not too bad in doing this. So adding more layers gives the networks more expressive power. That's part of the reason that these very, very deep networks can do really, really complicated tasks, simply put. Okay, let's look at some brain data. So I've put some data online that you can download, and I'm going to do and now I'm downloading it into this machine, and I'm going to try to do a very simple task. This data is pretty contrived. It's sagittal slices through data through brains, T1 weighted images from the IXI data set, and some of the data is flipped so that it's facing right, and some of it is flipped so that it's turning left, and I want to build a classifier that will tell me for each image, is it facing left or is it facing right? And I'm going to try to train a neural network to discriminate between these two cases. So I'm going to use, again, the sequential model as before, and densely connected layers, and it's going and crunching through the data. It's a little bit more data than before. And you can see that it does really, really badly in this case. Unfortunately, this network, even with its 2 layers, is just not strong enough to do this kind of classification. What I'll add in here to add to this is convolutions. Vince mentioned convolutions in his talk. Convolutions are filtering of the image with a weighting function. I have a simple example here that I'll show you. I'm going to skip over this a little bit, just for the sake of time. But here I walk through a really detailed example of what a convolution is. Let's look at a convolution of one of these brain images. In this case, I'm convolving this with a filter that doesn't do much. It smooths the data a little bit. But if my convolution instead looks like this, it's got a line, a horizontal a row of, it's a 3x3 filter with the first row being all negative 0.5, the central row being 1, 1, 1, and then the third row being all negative 0.5. When I convolve that with the image, what that does is it emphasizes the parts of the image that contain horizontal edges. I can also convolve this image with the same filter turned 90 degrees, which has then the vertical bar, and that then looks like this. It emphasizes the parts of the image that contain vertical bars. Convolutions are useful in neural networks because natural images contain correlations. For the same reason that they're useful in our own visual system, the filters that neural networks will learn will pick up on the correlations, the spatial correlations that exist in images. And those exist in natural images, but they also exist in images of the brain. Things that are further apart in the brain are more different than things that are close by to each other. Using convolutions in neural networks allows us to reduce the number of parameters in the first few layers of the network. So the first few layers of the network gain a lot of expressive power by reducing the parameters for every unit. And that's because if you think about the input of the network, it might be an image with 256 by 256 pixels, and if you had to learn a single weight for each one of them, that would be a lot of weights. But if instead all the unit has to learn is a 3 by 3 little window, that's just 9 parameters per unit that it has to learn for these relatively large input images. And that is how these convolutions save us parameters, at least in the first input layers of the networks. So here's how we express convolutional networks in Keras. We import this conv2D layer from the library of layers that exists in Keras, and then instead of densely connected units here, I use this conv2D. Again, I have 32 units of this kind, so each one of these units will learn a different set of 3 by 3 parameters for the convolution. I set the kernel size to 3 so that I have 3 by 3, and then I tell about the input shape and so on. I set the activation to ReLU, and then to pass that on to a densely connected output layer, I first have to flatten the results out between the convolution and the densely connected layer that follows. I can then do the training. This takes a little bit longer here because the data is a little bit bigger, and it crunches through. And I'll just cut to the chase that this doesn't really work that well either, and that's because this network is just not deep enough. So the following cell here will contain the implementation of a network that is deep enough for this problem. It's got 1, 2, 3, 4, 5, 6 convolutional layers, and in between convolutional layers, in addition to the activation, to the nonlinear activation function, the ReLU, there is also a max pooling operation that happens, and that's spatial pooling. The pooling operation takes the images and downsamples them by taking the maximal pixel in every little neighborhood of pixels. And I don't have much time, so I won't really get to the end of fitting this probably, but I will tell you that this one does this task rather well. So what I'll do now is I'll encourage you to go back and look at this notebook. As I told you, if you go to our website, the notebooks are linked from the schedule, and then there are the slides that I showed you before, and oh, here it is, it's done. Because it's running on a GPU, it runs pretty fast, and it's got 90% in this task. So to summarize, the building blocks that we use here are densely connected layers and convolutional layers. We stack those on top of each other into these sequential model objects. We use these sequential model objects fit method on training data with appropriate labels to do the training, and then we evaluate on separated test data and test label to tell us how well the network is doing after it's been trained. And so you'll see repetition of this pattern a lot in a lot of the talks that you'll see throughout the day when presenters are showing their own code. And before we move on to the next presentation, I'll be happy to maybe take a couple of quick questions if you have. If there are no further questions, then I will present the next speaker for this morning. Thank you.